23.3 Gauss Law. In this section, we will cover the key topics related to Gauss's law. We will start with an introduction to the law itself, followed by an examination of electric flux through both spherical and arbitrary surfaces. Then, we will look at how charges located outside a closed surface affect the total electric flux. Next, we will discuss the superposition principle and how it applies to systems containing multiple charges. After establishing these core concepts, we will dive into the mathematical formulation of Gauss's law. Finally, we will explore its practical application to charge distributions that possess a high degree of spatial symmetry. This overview will give you a clear roadmap of the fundamental principles we are about to explore. Gauss's law describes a general relationship between the net electric flux passing through a closed surface and the net charge enclosed by that very same surface. For the purpose of these calculations, we refer to this imaginary closed boundary as a Gaussian surface. Understanding this relationship is of fundamental importance when studying electric fields in physics. It provides us with a powerful alternative method to calculate electric fields. While we have previously used Coulomb's law, Gauss's law becomes especially useful and mathematically simpler when the charge distribution we are analyzing is highly symmetric. Let us consider a positive point charge, labeled as Q, located exactly at the center of a spherical Gaussian surface with a radius, r. Because of this spherical symmetry, the magnitude of the electric field is the same everywhere on the surface of the sphere. This magnitude is equal to the Coulomb constant times the charge Q divided by the radius squared. The electric field lines radiate outward from the positive charge and are everywhere perpendicular, or normal, to the surface of the sphere. At any specific point on the surface, the electric field vector is perfectly parallel to the local area vector. Therefore, the dot product of the electric field and the area element simply becomes the product of their scalar magnitudes. To calculate the net electric flux through our spherical Gaussian surface, we integrate the dot product of the electric field and the differential area over the entire closed surface. Because the electric field is constant in magnitude everywhere on the sphere, we can factor the electric field term completely outside the integral. The integral of the area element over the whole sphere simply gives the total surface area of a sphere, which is 4 times pi times the radius squared. We then substitute our previous expression for the electric field. The radius squared terms cancel out, leaving us with 4 times pi times the Coulomb constant times the charge Q. Recalling that the Coulomb constant equals 1 divided by the quantity 4 times pi times the vacuum permittivity, the 4 pi terms also cancel. We obtain the elegant result that the net flux equals the enclosed charge divided by the vacuum permittivity, epsilon naught. You might wonder if the size or shape of the surface matters. It turns out that the electric flux is completely independent of the sphere's radius. This is because as the sphere gets larger, the surface area grows proportionally to the square of the radius, while the electric field weakens inversely with the square of the radius. These two geometric effects perfectly cancel each other out. Now imagine closed surfaces of various irregular shapes surrounding our point charge, labeled as surface 1, surface 2, and surface 3. Notice that every single electric field line that passes through the inner spherical surface also passes through the larger non-spherical surfaces. Since flux is proportional to the number of field lines piercing the boundary, the net flux through any closed surface surrounding a point charge is always the enclosed charge divided by the vacuum permittivity. The net electric flux is exactly the same through all these surfaces, regardless of their shape. Now, what happens if the point charge is located completely outside our chosen closed surface? By examining the electric field lines radiating from the external charge, we can see that any field line that enters the closed surface on one side must eventually pierce the surface again to leave on the other side. This means that the total number of electric field lines entering the surface is exactly equal to the total number of field lines leaving the surface. Because entering lines contribute negative flux and leaving lines contribute positive flux, they perfectly sum to zero. Therefore, we can firmly conclude that the net electric flux through any closed surface that surrounds no charge is exactly zero. We can extend this logic to systems with multiple charges by using the superposition principle. This principle states that the total electric field is simply the vector sum of the fields produced by each individual charge. Let us look at a few examples. The surface labeled S encloses only charge Q1, so the net flux through it is Q1 divided by the vacuum permittivity. The surface labeled S' encloses both charge Q2 and charge Q3. Therefore, the net flux through S' is the sum of Q2 and Q3, divided by the vacuum permittivity. The surface labeled S" does not enclose any charges at all, meaning its net flux is zero. Finally, notice that charge Q4 is located entirely outside all of these surfaces. As we established previously, this external charge contributes zero net flux to any of the closed surfaces shown here. We can now state the generalized mathematical form of Gauss's law. It states that the net flux through any closed surface, calculated as the closed surface integral of the electric field dotted with the area element, is equal to the enclosed net charge divided by the vacuum permittivity. In this equation, the enclosed charge represents only the net charge strictly located inside the Gaussian boundary. However, it is crucial to understand that the electric field vector in the integral represents the total electric field at any given point on the surface. This total field includes contributions from all charges present, both those inside and those outside the surface. Also, keep in mind that a zero net flux could mean no charges are enclosed, or the net enclosed charge is zero. It does not necessarily mean that the electric field itself is zero everywhere on the surface. Let us solidify these concepts with a quick conceptual example. Imagine a spherical Gaussian surface surrounding a single point charge, Q. What happens to the total flux if we change certain parameters? First, if the enclosed charge is completely tripled, the total flux is also tripled, because flux is directly proportional to the amount of enclosed charge. Second, if the radius of the sphere is doubled, the flux does not change at all. All the electric field lines still pass through the larger boundary. Third, if we change the surface shape from a sphere to a geometric cube, the flux still remains unchanged. The exact same number of field lines passes through the closed surface, regardless of its shape. Finally, if the charge is moved to a completely different location, as long as it stays inside the surface, the flux remains exactly the same. Gauss's law depends only on the total enclosed charge, completely independent of its specific location within the surface. In principle, Gauss's law can be used to determine the electric field for any system of point charges or any continuous distribution of charge. You would simply set up the surface integral and solve for the electric field. However, in practical terms, performing this analytical solution is only feasible in situations that possess a very high degree of spatial symmetry. There are three typical symmetries that allow us to practically use Gauss's law: spherical symmetry, cylindrical symmetry, and planar symmetry. The trick is to carefully choose a specific Gaussian surface that perfectly matches the symmetry of the charge distribution. By exploiting these geometric symmetries, the dot product and the surface integral in Gauss's law can be simplified dramatically, allowing us to easily solve for the magnitude of the electric field. To summarize our discussion today, Gauss's law states that the net electric flux passing through any closed imaginary surface is directly proportional to the net charge enclosed by that surface. Mathematically, the net flux equals the enclosed charge divided by the vacuum permittivity, We learned that this net flux is completely independent of the chosen shape or the size of the Gaussian surface. Furthermore, any charges located outside the chosen closed boundary do not contribute at all to the net electric flux through it. Finally, it is critical to remember that the electric field vector in the integral formulation represents the total field created by all charges present in the environment, not just the field created by the isolated charges enclosed within the surface. Before we wrap up, let us consider 2 review questions to test your understanding. First, if the net electric flux through a Gaussian surface is calculated to be exactly 0, does that automatically imply that the electric field itself is 0 at every single point on that surface? Think about the difference between the net flux and the local field value, and how external charges affect both. Second, why is it practically necessary for a charge distribution to possess a very high degree of symmetry, such as spherical, cylindrical, or planar symmetry, when we want to use Gauss's law to calculate the magnitude of the electric field? Consider how spatial symmetry helps us simplify the dot product and pull the constant electric field term out of the complex surface integral. Take some time to reflect on these questions and ensure you can explain the answers clearly.